This is a video guide on using my time series data cleaning user interface. So to even get the program running, we want to open Visual Studio Code and open this app.py file. We want to make sure that our environment is properly set. So if we go here and we select an interpreter, we need to make sure that this interpreter includes all of these different imports so our Python environment needs to include all of these different modules. And also our Visual Studio Code needs to have the following extensions. So it needs to have Python and Shiny for Python. So once all that is done, I can click on this button here to run the Shiny app. And by clicking on this button here, I can open it in my browser. This is the first part of a video guide on using my time series data cleaning user interface. So to get started, we want to select a file by using this Browse button, which should be of CSV format. We can see that the separator is not properly chosen, so we're going to switch that to a semicolon. And now we have our columns in our visualization here. We can also set the header row in case we would want to, but in this case the first row is the header, so it's not really necessary. We can set the data types on the next page. So in this case, the date and the time give our timestamp column. So what we want to do is select both of them and then combine them by using this button. So now we have a timestamp column, which just merges them together. And next, we want to overwrite this datetime format to match with what is written here. So we can see here that the first value is a day, followed by a month, followed by a year, and then hours, minutes, seconds. So we copy this over in here, except with the right representations, which are here in the tooltip. And then we can convert the data. So the end result of this is that everything will be numeric aside from the timestamp column, which will be of datetime format. Other options we have here include generating headers. So this just renames everything to column 1, 2, 3, 4, 5, 6, 7, 8. We can delete selected columns. So now we're only left with 2, 3, 5, 7, and 8. In case we don't have any time data in our original data set, we can create a new timestamp column altogether. So let's say I wanted to go back from today's date or from Wednesday's date, and I want a sample rate of 1 minute, which is basically the same as my original data set. So now we have a timestamp with 1 minute differences between each of them. And if I also want, I could resample the data frame. So now we have 2 million instances, which is written right here. That's how many rows this data has. But if I want to resample it to have 1 point every hour, for example, so right now it writes me that there's the constant sampling rate of 1 minute. If I resample it to 1 hour, it calculates it again. We have 1 hour. And now, instead of the 2 million points, we only have 34,000. And this is also useful in case we don't have a constant sampling rate. So in case the time differences are not the same always. So then we need to do this before moving forward. But I just want to work on my original data, so I'm just going to reset the entire thing. I'm going to go back to date and time, combine them, and convert them back again. And now we're back where we started. 2 million points, timestamp, and all other things left the same. We can calculate prominent periodicities, so by clicking this button, and in this case, I'm just gonna stay with the default settings. So the end result tells us that each feature has a kind of periodicity. So for example, voltage has a repeating behavior every day, which is useful information. And here in the data input module, we can also do some sort of initial visualization. So I can, let's say I want to zoom out on my data. So if I click maximum samples on plot and set it to a very high value, I can see the entire time frame. So I can see that my data ranges from 2007 to 2011. Let's switch to the voltage data. This is what I have. And let's say I want to resample it, so 6 hours. So now I have much sparser points. And I can zoom in once again. So what we got for voltage here is that we have a repeating behavior every 1 day. So let's say I set this to 3 hours, which means we have a repeating behavior every 8 points. So if I click 80 here, this should have a 10-point periodicity within it. And I can see that there is indeed some kind of repeating behavior as I move along. So I can animate the plot as well by clicking this button. And also, if I want to, I can look at data next to each other. So let's say I want to visualize global active power next to voltage with our original sampling rate. And I can move across the time axis, see how these change. So that concludes the data input module. In the previous segment of my guide on my time series data cleaning UI, we finished the data input module. And as an output, we have all of our relevant columns converted to the proper data type. And we also calculated the prominent periodicities within each of these columns. So now we can move on to the missing value handling module. We can see that there are 71 continuous missing value instances. So for example, instance number 7 has a length of 3000 points missing. We can also see some kind of characterization of them. If we look at how these missing values occur over time, we can see, for example, that here at the end of 2010 we have maybe the most missing values. If we look over a span, so these spans are 144 days each. So this is the first 144 days of data, second, etc. So we can see that the most missing values occur in the last 144 days. And if we look at how these missing values are correlated, we can see that each of these features are perfectly correlated with each other in the missing values. So what this means is that if one feature has a missing value, another one will also have one. And for each of these plots, I can limit the plot size. So let's say I only want to look at these 3 variables, then I can see that. Or in here, if I want to do the same, I can see that, but these are perfectly overlapped, so I don't see anything different. Also, I can change the number of spans here. And then it updates this, telling me that, okay, now one span is only 80 days. Finally, I can do my imputation here. So if I click calculate, it's going to start filling these missing values in with something. And this is based on the prominent periodicities we calculated at the start. So I'll just leave this at the default value to calculate this, which is recommended. And now we can see our original data in red and the newly imputed values in blue. So if we go back here, we remember that number 7 is a long missing value. So we can go here, let's plot occurrence number 7. We can see that's how it's fit in. And we can zoom out, see how it fits into the context, and maybe switch to voltage. How is number 7 imputed in voltage? It looks like this. So, yes. This is a guide on the use of my time series data cleaning user interface. So in the previous segment, we finished missing value handling, and as a result, we imputed all our missing values, and it writes here, no remaining missing values. So now we can move on to data transformation. So we can see the runtime estimate for each downsampling rates. We can see here that if we go with the original sampling rate, the runtime is going to take 81 days, so we probably don't want to do that. And then let's say we downsample it to every 720th points, which means a 12-hour sampling rate. In that case, it would run immediately. Let's see how this would look like if we actually downsampled this to this. So we go here, we click on 12 hours, and we zoom the plot out entirely. This is how my data would look like if I resampled it. So, and this is my original data. So I lose a bit of information, or actually maybe a lot. But either way, I can select here based on this runtime estimate. And it also tells me what kind of periodicities I lose. So if we go here to the prominent periodicities, we can see that the submetering 2 has a 3-minute periodicity. So if we downsample it too much, we're going to lose this 3-minute. And even if we downsample it even more, we're eventually going to lose our 1-day periodicity as well. And it also tells us our new sampling rate in here and how much data points we have. So originally we have 2 million points, but if we downsample it to every 16 point, we're going to have 130,000. So here we can rename the folder to save in the desktop, and we can save our imputation results or our transform data. And this is going to result in a folder named such as this, data cleaning / whatever the folder name is. And our results are going to be saved here in data transformations for each of the different features of the data. This is a video guide on my time series data cleaning user interface. In the previous part, we transformed the data, and now we can move on to anomaly detection. We're going to select all of our transformed data by clicking on this browse button, and our data is transformed in one of these desktop folders under data transformations. So we're going to select all of that and read them. Now if I go over to voltage, I can see that this is the trend component, this is the seasonal, and this is the residual. And I can add them together to see how they look summed up. And this is my original signal. Now, by clicking on this button, I can compute anomaly detection. Here it is recommended that you have these original or default values. But if you have very few data points, then maybe it is recommended turning this sliding window size down. But aside from computing, we can also read in our results. So that's going to be saved here in anomaly detection results. I can select all of them. And now it's going to read it. And now, together with the transformation results, it's going to plot them next to each other. So if I go back to voltage, this is what I have with this BIC penalty calculation method. Let's say I want a less strict penalty. This is not strict enough. So then I click on this. This seems like a good penalty value. I can visualize different error types. So right now I'm only visualizing continuous errors. So this segment is one where the trend level is decreased. But I can also visualize point anomalies, also all of these together. Similarly with seasonal, except here I have different kinds of error types. So here I have amplitude levels decreased, point anomalies, shape anomalies, and similarly with each of these features. So what I need to do here is I need to select a good penalty type for all three of these different components. So for trend, seasonal, and residual. And that just depends on how the data looks good. So for example, this looks like a good penalty type, but this 1 to the power of -4 or 10 to the power of -4, this seems like it's too strict or too lax with its penalty value. So what I determined here is that a good penalty value here would be maybe this 0.04, and similarly with the other ones, let's say 0.01, 0.004, and now I can move forward with this penalty data. So now I can visualize how these errors are happening next to each other. So similar to missing value handling, I can see how they occur over time or over different spans. Once again, I can switch out the spans. But what's really useful here is how they are correlated. So let's say I want to switch to continuous errors, and between active power, voltage, and reactive power. And let's say I want to look at when the trend level is increased and when the residual is changed. So now I get this kind of correlation heat map. We can see some features are more strongly correlated than others. So for example, column 12 is strongly correlated with column 2. If we go over here, look at what 2 and 12 are, we can see that when global active power has an increase in trend, then usually global reactive power has a decrease in volatility. So these are the kinds of relationships between our anomalies. And similarly, I can see how these values are correlated between each other, but this time by taking actual values into consideration, not only whether one is increased or decreased, but by how much it is decreased. So here we see 1 and 9 has a good relationship. So it's when active power has an increase in trend, then usually voltage has an increase in seasonality. This is the last part of my video guide on the time series data cleaning user interface. So in the previous part, we selected to move forward with a subset of anomaly detection data by clicking this button here. And now we can move on to anomaly correction. So if we go over here to select a file, we want to go over here. We're in our household power consumption data, and we want to select our Boolean anomaly detection results. We open that, and we get this. And let's say I want to keep using my default values. So this tells me how much percent of each of the data sets I'm going to correct. So for voltage, I'm going to correct 4%, but my cutoff is 10%. So for example, here with submetering 2, I would have to correct 11%, but it won't correct it because I set my cutoff to be at 10%, so it won't do anything with this one. So if I click on calculate anomaly detection results, So with this completed, now it deleted a certain part of each of the data sets and put something back in its place. And how much it deletes and what it deletes depends on these variables, although at first it is recommended to just keep them at the default values. And if we go over here to visualization, we can see what happens. So for example, in global active power, the blue shows the corrected data and red shows the original data. For example, here we can see that in 2008 summer, it deleted all these points and rather chose to make a gradual change here rather than a sudden change. And this is because of the relationships between the features. So it's between this kind of correlation heat map. So what the computer detected here is that there is some kind of incongruent behavior. So it just chose to delete the data points and correct them. And now we can look at what kind of results I get from the data cleaning program. So by clicking this button and by clicking this button, I save different kinds of files. So I save relative anomaly detection results, which is a kind of data frame from the original data. Same with Boolean anomaly detection results and an error correction result. So I can use all of these to train machine learning models. And most probably they will improve the cleaning accuracy or the model performance by using these clean data sets. And that's it for the time series data cleaning user interface video guide. If you have more questions, I suggest that you consult the user guide.